Hello everyone. In this video we're going to discuss examples from Chapter 7, which is all about an introduction to hypothesis testing. My name is Fred Rispoli and I'm coming to you from Stony Brook University. So in particular we're going to look at examples involving stating hypotheses for testing and finding error probabilities related to the hypotheses. These examples are chosen from frequently asked questions and frequent errors on tests. In example 1, suppose we have an information technology company claims that a certain model of laser printers has a mean output capacity of 400 pages. A consumer report firm wants to show that the actual mean is smaller than what the company claims. Formulate the null and the alternative hypotheses. And in part B, suppose the report firm wants to show that the actual mean is different from what the company claims. Again, formulate the null and the alternative hypotheses. So a couple of key words here to focus on here is that here the firm wants to show that the mean is smaller than the claim, and in part B, it's simply different. So the null hypothesis for part A is that the mean is greater than or equal to 400. Right here we want this to be smaller. Notice the null hypothesis contains the equal component and is really just the opposite of what the alternative is, right? The alternative here is that the mean mu is less than 400, and you can see this is what the firm is trying to do. So here I've labeled this as the claim. Often the claim is the alternative hypothesis. In part B, suppose the firm simply wants to show that the mean is different. Okay? So now the claim here, still the alternative, but we simply write this as mu is not equal to 400. And the null hypothesis is that the mean is equal to 400. And as usual, the null hypothesis really is a statement that there is no change. Okay, now when we state hypotheses, there are two different types of errors that you need to understand well. So one way to think of this is, hypothetically speaking, suppose you knew the true state of nature. Of course, in most applications you do not, but for the sake of understanding the theory, let's suppose that one did know the true state of nature. So suppose in the true state the null hypothesis is true, and now we run a test. Well, the outcomes of the test would either be to do not reject the null hypothesis or reject. If the null hypothesis is true and our test concludes do not reject, then we got it right. But if the test concludes that we should reject the null hypothesis, then an error was made, and this type of error is what we call a type 1 error. On the other hand, if the true state of nature is that the null hypothesis is false, and let's just skip down here, and we determine from our test to reject the null hypothesis, we get it right over here. But if we do not reject the null when it's false, then we have it wrong. So there are various ways of thinking about this. Again, the type 1 error is the rejection of the null hypothesis when it's true. This is sometimes called a false positive in medical testing. The idea with medical testing is a test returns the result that there is an issue, okay, or some condition exists when in fact it does not. Okay, so that's a type 1 error, false positive. As we progress throughout this video, we will use alpha to represent the probability of making a type 1 error. The type 2 error is the failure to reject the null when it's false. Okay, so that's right here. We do not reject the null when the null is false. So this is sometimes called a false negative. And this has a probability that is given by beta. So there are various ways we could think about this, and it's interesting when we sort of move outside our course in probability. Think about one of my favorite examples involving medical testing. This is a nice way to try to remember these. So here on the left is an example of a doctor telling a man he's pregnant. Okay, so this would be an example of a false positive or a type 1 error. Okay, the doctor is telling the patient that he has a certain condition when obviously he does not have the condition. An example of the type 2 error would be here. We have a doctor telling an obviously pregnant woman that she's not pregnant. Okay, so this is a false negative. The doctor is saying that they do not have a condition, which is false. Okay, the woman obviously is pregnant. So these are some good memory aids for remembering these two types of errors. All right, let's apply some of these ideas now in the second example. Suppose a computer manufacturer wants to establish that the average time to set up a new computer is less than 2 hours. We want to formulate the null and the alternative hypotheses, ask what error could be made if the mean is actually 1.9, and a similar question if the mean is 2.1. All right, so a key word in this problem over here is less than. Okay, so the computer wants to establish the average time is less than 2 hours. So once again, we have the alternative here is that mu is less than 2.0. So in this case here, we might say that this is the claim once again. Okay, and then the null hypothesis would be the negation of this. If this is not true, then the mean is greater than or equal to 2 hours. Again, notice the null hypothesis always contains the equals component. So these would be the testing hypotheses. Now, suppose we know that the true mean is 1.9. All right, if we think of this with respect to the hypotheses we gave in part A, so if the true mean was 1.9, you could see this would mean that the null hypothesis is false. So the question is, what error could be made if mu is 1.9? Well, when it's 1.9, the hypothesis is false. So when the null hypothesis is false, we could only make a type 2 error. Right? When it's false, we either get it right or there's a type 2 error. So the correct answer to B is a type 2 error. On the other hand, if the true mean is 2.1, okay, now looking at these hypotheses, we see if the true mean is 2.1, then the null hypothesis is true. So we could look down this column, and if we're trying to figure out what type of error can be made, you could see that is a type 1 error. All right, so at this point, I suggest that you read through this exercise and stop the video. See if you can get these answers. The problem is at an airline. claims that the typical flying time between two cities is 56 minutes. For part A, we want to formulate the hypotheses with the intent of establishing that the flying time, the mean flying time, it's important to remember, we're talking about means here. The mean flying time is different from the published time of 56 minutes. Okay, so we want to state the null and the alternative hypotheses. Part B, if the true mean is 56 minutes, what error can be made? Explain your answer. And similarly, what error can be made if the true mean is 50 minutes? So at this point, stop the video and let's see what you get. Okay, did you get that the null hypothesis is the mean is 56 versus the alternative not equal to 56? In part B, the type of error that can be made is a type 1 error, because we know that when the mean is 56, the null hypothesis is true. And in part C, a type 2 error. Okay, so this problem reminds me of course, flying. We have this brand new, I don't even know if these are out yet, Boeing 787s and Come Fly With Me, famous movie and song. On to example 3. Suppose the lifetime of a certain type of car engine is normally distributed with a mean of 200,000 miles and a standard deviation of 30,000 miles. An automaker claims that the new year model has an engine with a longer average lifetime. Here we see a car engine. A sample of 16 cars with this type of engine from the new model is obtained for a test. The rejection region would be that the sample mean is greater than 215,000 miles. Okay? So when a sample is taken, the sample mean is calculated. If that sample mean is greater than or equal to 215,000, the null hypothesis would be rejected. So our first step is to identify the hypotheses. Then we want to do some probability calculations of a type 1 error, and then a probability calculation of a type 2 error. Okay, so we start with the null hypothesis would be the mean is less than or equal to 200,000 versus the alternative, the mean is greater than 200,000. So let's just back up a second and identify the key word here. So here you could see this sentence. The automaker claims that the new year model has an engine with a longer lifetime. So we would use that to identify our alternative hypothesis, and then the negation of this is our null hypothesis. All right, now in part B, we're asked to calculate the probability of a type 1 error, or alpha. Okay, so the first thing we need to do is identify the appropriate probability distribution for x bar. Okay, so we start out, we think of the random variable x as the lifetime of an engine. We assume that the average is 200,000. Okay, so here we're sort of, under the assumption of our null hypothesis, the mean is 200,000. So we know that x bar follows a normal distribution. Okay, the mean is mu, and the distribution of x bar has a variance sigma squared over n. So we think in terms of this normal distribution. Now we could use this to calculate alpha. So we want to find the probability of rejecting the null when the mean is 200,000. All right, well, we go back to our rejection region. Remember, we said over here, we're going to reject when x bar is greater than or equal to 215,000. Okay, so this is the probability now that we need to calculate. So we get the probability z is greater than or equal to 215 minus 200,000 over 7,500. So this is the standard deviation for the x bar distribution. So this works out, this fraction simplifies to just a 2. So we want to find the probability z is greater than 2. So we could use the complement and calculate 1 minus the probability z is less than or equal to 2. Okay, so less than or equal to 2. So I could use phi of 2 here, which sort of just denotes the fact that we could use our table of normal probabilities. So we get 1 minus 0.9772. So let's just confirm where that number comes from. We have z is exactly 2.0. So inside this red circle, you'll see here 0.9772. So that's where we're getting this number, and then we work out the subtraction. So we get alpha is equal to 0.0228. So that would be the probability of making a type 1 error. Okay, so this would mean this is our chances of rejecting the null when the mean is actually true. Okay, or rejecting this, I should say, when the null hypothesis is true. All right, now in part C, we're interested in finding the probability of a type 2 error, or a beta, as we use the notation. So suppose further that a study establishes that the true lifetime, the true average lifetime of the new engine is 210,000 miles. Okay, so we want to find the probability of a type 2 error. Okay, so if it's 210,000 miles, you could, first think in terms of, well, what does that mean here? Okay, well, it means that the null hypothesis is false. Okay, and you could see over here, if the mean is 210,000, the alternative is true. Okay, so if we go here, we now have to adjust our normal distribution slightly, okay, because now we're assuming that the new mean is 210,000. So the type 2 error probability is, we'll use the notation beta of 210,000. So in here, this is what we're assuming the true mean is. Okay, again, beta is the probability of a type 2 error. So this is the probability that we do not reject the null when mu is equal to 210,000. So that would be our type 2 error. And now we have to think, all right, when do we not reject the null? Well, we go back to the rejection area, right? We go back to this right here, okay? So x bar is not rejected when x bar is less than 215,000. So that's where we get this from. I want to find this probability. X bar is less than 215,000. So we work this out as a normal probability. We set up this fraction. This is my x minus mu over the standard deviation for x bar. You could see this fraction, if we round it off to 2 decimal places, right, this is going to give us a z value. And in order to use the table, we need it rounded off to 2 decimal places. So I'm going to take this fraction as 0.67. And now we could look up our probability in the table. You could see here, I've mentioned that it's in the blue circle, so up here. So I take 0.6 would be this row, and the second decimal place is 7, so I get 0.67 right here. 0.7486 is what we get, and that is our final answer. So that's the probability of a type 2 error. All right, in example 4, we're going to examine error probabilities once again, but this is sort of a variation of what we were doing, perhaps in some ways an inverse problem. So suppose that it's desired to test a null hypothesis that mu is equal to 100 against the alternative mu is greater than 100 pounds on the basis of weights of a random sample of size 40. Suppose we know that the population has a standard deviation of 12 pounds. So the question now is, for what value of x bar must the null hypothesis be rejected if the probability of a type 1 error is to be alpha is equal to 0.01? Round off to 1 decimal place. So here we're given the alpha probability and we're asked for the x bar. You could see how it's just sort of the inverse of example 3. In example 3, we were given a value for x bar and we were asked to calculate alpha. Okay, and then just for further clarity, part B asks us to sketch the graph of the probability. So let me point out that since n is greater than 30, we know by the central limit theorem that the distribution of x bar is normal. So we know we could use this equation for z, x bar minus mu, divided by sigma over the square root of n. Remember, this is the standard deviation when we talk about the distribution of x bar. So the first step is to find the appropriate value for z. Right? We're going to use this equation, and really we've been given mu, we've been given sigma, we're given n. So if we find z, then we can solve the equation. All right, so what do we know about z? Well, we know we want alpha to be equal to 0.01. Okay, so alpha represents a right tail probability, but our tables give the cumulative probability, so we need to think in terms of the left tail, and if the right tail is 0.01, that leaves a probability of 0.99 in the left tail. So what we can do is use the table in reverse. So here you can see I've said we get z is 2.33, and I've identified this on the table with the purple circle. So let's take a look. Okay, so right here. So the idea would be I'm searching the table, right? I sort of start in here first, and I try to get as close as I can to 0.99. So you could see here we get pretty close, 0.9901. Right? It's closer than either of these two numbers. So now I have to find the corresponding z. So I go over here, I get the 2.3, and in this column we get the second decimal place. So we get 2.33. for our z value. Okay, now we have an equation that we could work with. We take this equation, solve it for x bar. Okay, you may want to stop the video and just go through those calculations. They're not too bad. Okay, and when we round off to 1 decimal place, we should get x bar is equal to 104.4. Okay, so this gives us the benchmark that we're going to use to reject the null hypothesis. Now, another way of seeing this is by sketching the distribution plot. So here I used Minitab to do this, but we don't have to do this with the technology. You could simply sketch a normal curve. Okay, we were given 0.01, so I think of this as the right tail probability. Remember, we had the intermediate step that you don't see here. Z was 2.33. That's the Z value. That gives 0.01 on the right and 0.99 on the left. Okay, and then we convert that to our x bar. We get 104.4. Okay. Again, the one thing here you have to remember is we're looking at the distribution of x bar. So the mean we assume is 100, but x bar has the standard deviation 12 over the square root of 40. Again, that comes from the central limit theorem. Okay, so as we move on to hypothesis testing in a little while, you'll see that this region in here, this sort of represents our rejection region, or we may call this a critical region. And then everything sort of to the left here is an acceptance region. All right, so this problem has a lot of opportunities for some what-if changes. So here's a stop the video exercise, and my part A is for what value of x bar must the null hypothesis be rejected if the probability of a type 1 error is to be alpha is 0.05. Right? In the previous version we had 0.01, but what if that changes? How does the value of x bar change? Again, let's round off to 1 decimal place. Sketch a graph of this probability and label it with all the important numbers. And now in part C, suppose we go back to the original statement and change the alternative to mu is less than 100. Right? In the original problem, it was greater than 100. If we change that, and then we try to solve the problem as originally stated, okay, we want the probability of the type 1 error to be 0.01. What value of x bar do we use? Okay, so stop the video and let's see if you can get these answers. All right, for part A, did you get 103.1? This would be your final answer. All right, the way we would get this is we have to sort of recalculate the z value. Okay, the z value that we need to have an alpha of 0.05 is 1.645. Let's see, I believe I have this here in my table. If not, we'll look right over here. We want 0.95. So 0.95 would be right between these two. So you'll see 1.645 is the appropriate z value. Okay, so now what we do is we solve the equation as before, and that's how we get 103.1. If we sketch a graph, the graph would look something like this. We'd have our bell curve, same mean and standard deviation as before, but now we have 0.05 in the tail, and that gives us an X bar of 103.1. Now, in part C, we could describe this by saying, well, now the test is a left-tail test, right? It's a one-tail test, but in part A, it was a right-tail test. In part C, it now becomes a left-tail test. Okay, so what's the correct Z value? We're still using alpha as 0.01. So our Z value, we have to look at the normal probabilities on the table that has negative Z values. Okay, so now I'd be interested in finding the value that's closest to 0.01. So you could see this is the closest one. It's a little bit better than this one. So now we simply use minus 2.33. Okay, so if we work that out, same equation as before, we get X bar is 95.6, and this would be a sketch. And again, this will be what we'll call the critical region. Okay, so this concludes the video. I hope you learned a few things from watching it.